Hello, all, and welcome back. We are getting into, I think it's chapter 25 now. Yeah, chapter 25, where we're talking about sort of the fundamentals to what I think is the most interesting part of the chapter, the part that I have studied most in my undergraduate electrical engineering career at UTD. If you study electrical engineering or computer engineering or mechanical, you will hit this pretty hard again. Computer science, software engineering, maybe a little bit more, but you're all here taking physics 2326, so you're all going to at least have to have a rudimentary exposure to it. Okay, so what is current? Well, let's talk about it sort of conceptually for a second. Say you have a battery here. All right. Now, what we've been doing just now is we have a capacitor and we make this connection, and the capacitor stores a charge on the plates. Okay, and we've been going over a lot of that, but current is something else entirely. What happens with the capacitor is we basically, at least for the purposes of what we've been doing, we say that the charge immediately, or at least fast enough, gets on the plates and it stores a charge. Then that creates a potential across the plates. A charge at potential means we have potential energy measured in joules, and we can hopefully do something with that. Now, with current, we're talking about the charge actually moving through a circuit. Okay, we're not just talking about, okay, we connect it and then boom, we store a charge there. We're interested in a kind of a flow over a certain period of time, and that brings me to the mathematical declaration of what current is. It's the first derivative of charge with respect to time, and that's measured in a unit called amperes. I think there may be an accent on that. Um, it doesn't matter because you'll never call it amperes, you'll call it amps. Anybody who calls it amperes is being extremely posh or just like really, really wanting to come off as maybe smarter than they actually are. Um, just call it amps, please. If you call it amperes, I'll know that you just learned about it yesterday and you didn't watch this video. So anyway, amps are the rate of flow of charge with respect to time. So it's like how many coulombs go past a certain point in a second. That's what an amp is. Okay. Amp is a scalar unit. It is not a vector quantity. Current's not a vector quantity. It either goes this way or that way. Forwards or backwards. Um, and hence positive or negative by extension. It's not a vector quantity, but you will see it combined with vectors quite a bit here. And you also have a unit called current density. Current density, which is measured in amps per meter squared. And it's the amount of current that it doesn't go necessarily go past a certain point in time, but if you have a conductor like this and the current's going this way, and you take a cross section of it, say it's a circular cylindrical wire, then you've got a circular cross section with radius r, and the area, of course, is pi r squared. So the the amps, don't be confused here when I do a capital A here. It's actually, I should just say, just to be totally clear, maybe I over meter squared. Okay, so current over area is the thickness, the density of current. That you could get really thick with it, or just have a little bit of current flowing through. But there is a vector quantity there because we associate it with a drift velocity. And the drift velocity is just how much net charge is flowing past this given point. It's kind of like the fundamental unit we're dealing with here. Now, what happens with the electrons when they're flowing is they kind of bounce around an awful lot. So you've got a whole bunch of them just doing different paths and kind of just being bonkers, maybe even going backwards a little bit. But your current is the net flow of those electrons. Because, if your current is flowing this way, that means that more electrons are passing a given point heading this direction to the right in this case than the left. It's kind of like traffic flowing. If it's rush hour and it's 8 a.m., there are more people going southwest on Central Expressway, or I guess technically I'd call it south since it's an odd numbered highway, than there are going north. There are more people going into, or from McKinney, say, there are more people going into Plano and Dallas than going the opposite direction. Though, plenty of people work in McKinney now too. So anyway, that's what the drift velocity is. And then Q is just a unit of charge that's quantized within, meaning, how many Qs do we have? And usually Q is the elementary charge, which of course is just, what was it, 1.6 times 10 to the negative 19 joules. I'm sorry, coulombs. Coulombs. All right, and then your N would just be like your number of electrons or your free electrons. And those are the mobile electrons that you have in a given substance, like say copper, which is a very common conductor. And then, those many electrons are the ones that are going to be moving if that's what you're using. And the drift velocity will also contribute to the measure of your current itself. So, and then Q, like I said, is normally the elementary charge. And that's current density, okay? Not current, but current density. Because what we haven't accounted for is how wide our pipe is that we're going down. So current is actually going to be current density times area, okay? So, and again, just to keep from being confusing, I'm going to say meters squared. All right, and then of course that's going to be number of electrons times the charge of those electrons times the velocity of those electrons times the area that they're going over. So, cross-sectional area. And then you're going to have your current. So N is just going to be a number, a quantity over a unit volume, because it's like the free electrons that are, encompassing this particular conductor that's a given length and then has a given cross-sectional area, right? So number of electrons, let's say maybe number of E per unit volume, times charge, which is going to be measured in coulombs, times drift velocity, which is in meters per second, times the cross-sectional area, which is obviously meters squared. And then you can cross some stuff out here. And you're going to be left with number of electrons times the charge of one electron. So your total charge is going to be these two together over seconds or unit time. And that's just the same thing as that is the change of charge or the flow of charge over unit time. So that's how you find current from those two different formulas. And we're gonna get pretty deep into this, and we're gonna see just exactly what we can figure out from this. Please come to my SI session Tuesday at 4 o'clock in MC 3606B, and we will talk about this, maybe a little bit more on capacitance, and I look forward to the lectures this week. Everybody have a good one.